Hello and welcome to the eBPF and Cilium office hours. Today is episode 7. Hasn't time been flying? If you're joining us live, do say hello in the chat. It's always good to see you here. I see Magno's already here, so hi to you. I hope everyone is doing really well today. I have a couple of special guests. My main guest I will be introducing shortly, but I also wanted to mention EB, my new eBPF bee that arrived this week. Love this bee. Hi Alex, good to see you. All right, let's get started. I don't have very many headlines to share today. It's been quite a quiet week in terms of eBPF news. But what we do have, there is a new release of Red Hat Enterprise Linux with kernel version 4.18, which has some eBPF features in it. So good news for enterprise users who want to be using eBPF capabilities. And the other link that I'm going to share in the show notes today is this nice blog post about routing traffic, or routing, depending on which part of the world you're in, routing traffic in Rust with eBPF. I personally have only done a little tiny bit of Rust programming, but I did really like it as a language. So I think it's going to be really interesting to see more and more people writing eBPF capabilities with Rust. All right, hi to John. Thank you for joining. I can see there's a few more people out there, so do say hello if you're with us live. We love to hear from you. Hi, Marino. Great to see you. I think you have been with us every show. I think Magno might have been with us every show. I think Alex might have been with us every show. So great to have you with us. All right, so I think that it is about time that we move on to the main topic for today. I'm delighted to introduce our guest today, who is probably one of the world experts, if not the world expert, on DNS, which is our topic for discussion today. So let me welcome to eCHO Laurent Bernaille from Datadog. So great to have you with us, Laurent.
Hello, I'm very happy to be here today. And I mean, when you contacted me, you had me at DNS, right? You know, I love and hate DNS at the same time, as many people, I'm sure. And I'm by no means a worldwide expert on DNS, but I definitely have a story to share about DNS, especially in the context of Kubernetes, because I work at Datadog and we've been operating pretty large clusters. And DNS has proven to be an interesting beast, to say the least.
Absolutely. So if you haven't already checked out some of Laurent's talks, we're going to link to at least one of his KubeCon talks where he's talked about some really great horror stories and exciting things that have happened through the use of DNS. So yeah, do ask us your questions. We have Laurent's expertise. Make the most of it if you have questions about DNS. I think we should start at the beginning. Perhaps, Laurent, you can tell us a bit about what DNS is. I mean, apart from domain name resolution, let's take it from there.
Sure. So I'm going to share a very simple slide explaining DNS. Okay, here we go. I mean, if you look at in Wikipedia, the definition of DNS is that it's a hierarchical and decentralized naming system, which is completely true, but also not very helpful, right? So the most common use case is what I put at the very top of the slide, which is transform names we can remember into IP addresses. But DNS can do far more than that and can store many different types of information, but IP addresses are by far the most common one.
In Datadog, do you use any of the other kinds of things that the DNS could store?
We do, because some of the other records are records you have to use, like for instance, name server records, which are records telling you what servers are responsible for a given domain, for instance.
Okay.
And in some cases, we use PTR records, which are the reverse, right? You can ask what is the name behind an IP address, and it is usually used when you want to validate a certificate, for instance, because you receive a packet from an IP address saying, I have this certificate with this name, and some clients will verify that the IP used in the query is actually matching the name in the certificate itself.
I didn't know that it did that. That's good to know. All right. So I think you had a diagram you were about to show us, and I asked you a question.
Exactly. So, I mean, this is a simplified view of DNS because DNS is very complicated. But what I wanted to highlight is the most important parts and the one that we will talk about when we talk about it in the context of Kubernetes afterwards. So usually it starts with an application requesting a connection to a specific domain. And the way applications usually do that is they use a POSIX call in the system, which is get ADDR info with the name. And then this is managed by the libc on the system, which is going to do a lot of magic under the hood, right? It's going to look at the resolution configuration on the host using the resolve.conf file. And then it's going to query the DNS server that is configured inside this file. And one of the way it works, it's quite often, is that the first server you hit doesn't know about anything yet, but it knows how to forward queries and how to cache results. And caching in DNS is very important, right? Because it's designed to be decentralized. And the way it's efficient is because at every single layer, every single component involved is heavily caching. And this is how we can query so many domains and have efficient answer. And so this forwarder is usually forwarding traffic to a resolver that is doing a recursive resolution, which is basically taking the name. So in that example, www.com, and trying to see which IP address is behind that name. And to do that, the first thing a recursive resolver will do is ask root servers who is responsible for .com. And the root server is going to answer to give a list of IP addresses, which are IP addresses of server responsible for .com. And as you can imagine from the name recursive, then the resolver is going to contact the servers responsible for .com and ask them for which servers are responsible for google.com. And with the answer, it's finally going to get to the last one and ask the google.com name servers what are the IP address or IP addresses behind that name. And since these servers are responsible for the google.com domain, they know and they will answer, and the query will make it back to the client. And of course, at every single step in this, you have caches, right? So it's very unlikely that your recursive resolver, for instance, will query the root servers more than once in a while because it's going to cache these results.
So why is DNS such an important part of Kubernetes?
So in one of the things I like to say about Kubernetes and DNS is when you take on the task of managing Kubernetes clusters, you know you're going to be managing API servers, controller managers, kubelet, all these things we know about in the Kubernetes ecosystem. What you usually don't realize at the beginning is that one of the most critical services you're actually going to manage is DNS. Because all the Kubernetes control plane components are of course critical, but if they are down for a few minutes, it usually doesn't impact existing applications, right? All the pods are still running, they have connectivity, they can do whatever they need. And as long as you fix the control plane fast enough, nobody even notices what happened, right? However, when there's a glitch in DNS, it can impact applications immediately in a matter of seconds, and you can have a severe outage very fast.
I mean, I guess pretty much every time any pod wants to make any kind of network communication, it's going to have to make a DNS query. Is that?
Yes, it's very likely, and later we talk about how applications can can be designed in a way to be more resilient to small DNS glitches.
Right. Just want to say hello to a few more people who've joined. Tobias, I'm not sure if I already said hello to you. Russell, Noel, great to see some more of these regular viewers. Anderson, great, thanks for joining us. So we have also started getting some questions in, and the first question is, I think what this whole episode is trying to answer, which is, why is the network problem always DNS? That did come with a little smiley face, so... And I think it is true that a lot of the time it is DNS that's responsible for issues. One question, I don't know if we'll come to this later, but I will ask the question now anyway from Marino. What are some best practices for DNS with multiple Kubernetes clusters? Does service mesh with service discovery fit the bill?
Well, this question is a pretty difficult one. I think we'll touch upon it later.
Okay.
And if I don't remember to, can you ask the question later when we've seen why it's complicated, right? Because right. I mean, we're going to start from the basics, and then we're going to go to the more complex parts. And this one is definitely part of the most complex ones.
And I think one of the reasons why at Datadog you're hitting, you know, you're operating at a scale that means you're quite likely to hit DNS issues more frequently than perhaps some of the rest of us do. So what kind of things do you start to hit when you're operating at scale?
So the most simple problem you can get is just that you're not able to serve the volume of queries you get. To give you an order of magnitude, on the large clusters we operate, we serve tens of thousands of DNS queries per second. And so, of course, you need to make sure that the infrastructure backing this service is scalable enough. So you have no problem, right? And applications serving DNS queries need always to be up to be able to serve all these queries. And of course, at this type of volume, you need to be very careful when you do rollout, for instance, and when you update your DNS infrastructure, because some applications react extremely poorly when you lose even only 1% of DNS queries.
So I think you've taken a few different measures that you've spoken about in some of your talks about trying to reduce the number of queries. So maybe you can talk us through a few of the ways that you've done that.
Yes, if it's fine with you, I was about to show how DNS works within Kubernetes.
Oh, sure. Sorry.
That's completely fine. Because I mean, we've talked about DNS, but of course, in Kubernetes itself, it's set up in ways that make it a bit specific compared to usual designs. So for people familiar with Kubernetes, right, when you configure a kubelet, you actually tell the kubelet what the DNS configuration is, and what the kubelet will do is it will inject the resolve.conf file I mentioned earlier into the pods. And here I give an example of what it looks like, right? Which is something that is, a few things in that file are pretty uncommon compared to what you usually see on servers. So the name server line is actually very similar to what you would see in a standard server, right? It's just an IP. In this case, it's the IP of the DNS service in the cluster. And you have many search domain, which is not common, right? And the reason you have many search domain is so you can do things like connect to this service and just put the service name. And if you look at the first domain in the search domain list, you can see that it's namespace.service.cluster.local, which means the resolver will try and add this suffix to the name. And if you're trying to connect to a service in the same namespace, it will work. And then you have the other, which allows you to connect to any service in the cluster with a short name and to everything you can address within the cluster. But to make this work, you need the final option, which is one of the trickiest options in Kubernetes, which is n.dots =5, which, I mean, it's not a very familiar option because it's usually the default is 2, and this is what we have on most servers, right? And so most people, I mean, in my case at least, I wasn't really aware of what it was doing before Kubernetes. And so what it does is this says to the resolver that if you're asked for a name with less than 5 dots, then you can try all the search domains. And that's important because, for instance, if we get back to our example from before, like www.google.com, this only has 2 dots, right? Which means for www.google.com, we're going to hit all the search domains first.
And then once it's tried all those kind of prefixing what you're searching for plus those search domains, eventually it will get to a point where it will say, okay, I'll just try the 2-dotted www.google.com, and that's the point where I'll get the result. Yeah.
Exactly.
So we've made 4 redundant queries before getting to the one that's going to be useful. And in terms of how it works, because we were just before focusing on the pod and the result and how it's configured. But usually what you do is you run a DNS deployment that is fronted by a Kubernetes service. And in the past, people used to rely on kubedns, and most people now are using core DNS, which is what we've been using for quite a while. And the way your container is accessing the service is actually what always happens in a Kubernetes cluster, right? You use a proxier, which can be kubeproxy or Cilium, which is what we use. And this proxier is responsible for transforming the cluster IP of the DNS cluster IP to a pod IP. And so you can get load balancing, which is one of the way, of course, you can scale by having multiple pods backing the DNS service. And in terms of configuration, what is important, and that is why we had the first slides explaining the different components in DNS, is that core DNS pods are authoritative for cluster.local. So what they do is they connect to the API server and they watch all the services in the cluster and they create entries. So for this service name, the service IP is this, for instance. But these DNS servers are only authoritative for cluster.local, so only for the cluster. So any query for anything else is forwarded to an upstream resolver, which, depending on your setup, can be the resolver of your cloud provider, for instance. Okay.
And I think the next slide is, yes, so we talked about ndot before, right? So it's a very simple example, right? And if you're in a namespace matrix and you're requesting a service called points doesn't have 5 dots. So we're gonna hit, the resolver is gonna add the first search domain that I showed before, and that's perfect, right? We get our answer. If you're in a different namespace, what you need to do is, if you're used to Kubernetes, right, you need to specify a service name.namespace. And of course, the first search domain is not going to make sense, right? Because you're going to have a namespace named twice. So in this example, if you're querying points.metrics, the resolver is going to add the first domain, which is logs.service.cluster.local, because the querying pod is in the logs namespace. This doesn't make sense. So we get an NX domain, which is DNS server telling us, I don't know about this name. And the resolver is then going to continue with the second domain. And if you remember from before, it doesn't have the namespace this time. And this time it's going to make sense and it's going to answer. And what we started to allude to before is that, well, that is a theory. In practice, it's actually looking pretty bad, right? So here in this example, here is what happens. And this is actually captured on the test host, right? When I prepared this slide, which is you're in a pod and you're requesting www.google.com. And so you need to iterate over all the search domain first, and then hit default domain. But what makes it worse is, as you can see on this example here, is that we're querying both for IPv4, and these are the lines with just an A, and IPv6. And these are the lines with 4 A's. And of course, this has many consequences, right? Load on the infrastructure, because for a single query, you're actually doing 12. Also latency on the client side. And the worst part is if any of this query or the answer to the query is lost, the resolver is going to wait 5 seconds by default, which means, of course, for the client, it's not great, right? You're trying to connect to a domain and you have to wait 5 seconds before you get an answer.
Right.
And yes, and I think we've covered most of the things that are important in the context of Kubernetes, right?
And I guess the load that you're going to have into, you're going to have a significant proportion of your traffic is going to turn out to be DNS queries.
Yes, that have no answers, right?
Right.
Like, it's actually something that's interesting, because if you look at the metrics on your DNS servers, one of the things you look at is the answer type, and you expect answers to be success most of the time. But depending on what you access in your Kubernetes clusters from your pods, it can be that most of the traffic is actually NX domain. So DNS service telling queryers, I have no idea what you're asking me for. And I think in many clusters, I'm not sure where we are now, but this was definitely more than 50% of the traffic.
Wow. So can that make it difficult to tell when you have a real DNS problem compared to, oh, no, this is just normal NX domain responses that we expect?
It's very difficult to use NX domain as an indicator of a problem, because it's actually normal in the context of Kubernetes to get quite a lot of NX domain answers.
Right. Yeah. So what did you do at Datadog? You've had to deal with this scale. What kind of approaches have you taken?
We did a few things. The first thing is we tried to measure, right, and observe what was happening in the clusters, and to make sure that we had enough pods to serve DNS traffic. And to do this, we use auto-scaling. We use the proportional autoscaler in Kubernetes, which means for every 100 calls in the cluster, for instance, or every 100 hosts, depending on how you want to configure it, you have to create one pod.
One DNS pod.
One DNS pod, exactly. Right. And of course, it's not perfect. It would probably be better to do proportional autoscaling based on the number of queries you get. But we found that it's actually better to have a stable number of pods, because if you do autoscaling based on number of queries, you're going to add and remove pods very frequently. And the problem is, every time you do that, you tend to lose DNS packets.
Right.
So it's important to have enough pods, but if your infrastructure is not moving too much, it's likely better.
Right, because every time you lose a DNS packet, you risk the querying client having to wait for 5 seconds before it times out. Yeah. All right. You've talked quite a lot in conference talks and Kubernetes KubeCon about horror stories. What do you think? What's your favorite horror story that you've hit?
So I think my favorite one is the weirdest one, which is one that drove us a bit mad, to be honest. And I'm going to tell this one. It's a bit complicated because it's low level DNS, so don't hesitate to interrupt me and ask me for clarification, right? So what happened is we updated core DNS one day from version X to version X plus 1, for instance. I can't remember the exact version numbers. And everything was working completely fine. So we were doing this one cluster at a time. And well, we were good, right? And at one point, an application reached out to us and they told us, well, we can't connect to Postgres anymore in this specific cluster. And it started at this exact time. And this was perfectly lining up with our DNS rollout. So of course, we rolled back, it fixed the problem, but then of course we had to understand what had happened. And this is where it gets completely, this is where it's weird, right? So in DNS, when you do a query, it's usually using UDP. And the problem with UDP is you have a size limit of 512 bytes by default for DNS, and you can only fit a certain amount of data in there. And if the number of answers you have in your DNS answers, because you have many IPs, for instance, and additional headers giving you additional information, you can go above this limit. And in that case, the way it works is the DNS server is going to give you an answer over UDP, because of course you asked over UDP. It's going to be a partial answer, and it's going to set the truncate bit, which is a bit in the header of the DNS packet saying, here is an answer, but it's truncated. And if you want the full one, what you should do is upgrade to TCP, where you will get the full answer. And we discovered that our applications were connected to Postgres using pgbouncer, which is a proxy to aggregate connections to Postgres. And that pgbouncer was using a very specific resolver. So instead of using glibc, which is a very common one, it was using a resolver called evDNS, which is an asynchronous resolver. And resolving asynchronously is actually a very good idea, right? Because it avoids having to do a DNS query every time you make a connection. So it's very good because if you have a glitch in DNS, it means you can still connect to an IP because you've done resolution in the past and you will retry in the future.
It's so like it's a great idea. Cached, you'd still have the result from your previous query.
Exactly, yes. And the most important thing is you don't have to do the query when you want to connect, okay, which is the worst, right? Because if you have to do the query and it fails, then you can't connect.
Okay.
And so it's a very good idea, except it's written in documentation that evDNS doesn't support upgrading to TCP. And so what it does is it's just dropping the answer. If it receives an answer with a truncate bit set, it considers this as no answer and fails. And so we realized the problem, and so we recompiled pgbouncer to use another DNS, which is CRS, if I remember correctly, which is also asynchronous, but supports upgrading to TCP, and it was fixed. I mean, and of course, it's very weird. Why? And because why would upgrading core DNS cause this problem? Well, it turns out we had a second problem, which is that there was a bug in core DNS where in certain cases, it was not setting the truncate bit. And this bug had been fixed between the two versions. And so suddenly core DNS was setting the truncate bit, which triggered the problem in our application.
Because that resolver didn't know how to deal with that truncate bit. That's
exactly.
Cool. And I think that kind of leads us on, unless there was anything else you wanted to say about that particular story, but it leads us on to thinking about how resolvers are different. And I think this was another thing when we were talking beforehand was quite surprising to me that, you know, not all, you think, oh, I'm just making I'm making a network request and under the covers DNS is happening, but you don't expect it to behave differently depending on the distribution of Linux even that you're on. So tell us a little bit about the different resolvers.
So this is one of the things we found the hard way, right? So I was very careful in the first slide, and I mean, you may have noticed that I didn't write glibc when I did an arrow between the application using get ADDR info. I just wrote libc because it could be any POSIX implementation of libc, right? And different distributions have different implementations and they do different things. So one of the biggest difference we've seen is that glibc, so the one that's very common and that's used in Ubuntu, for instance, is doing things very differently than Merzel, which is the libc used in Alpine. And we haven't used other libcs, but I wouldn't be surprised if they still did things differently. Even worse, if you're using Go applications, for instance, well, Go has its own native libc implementation, which also behaves differently. And even when it calls the libc, so if you use cgo, it calls it with non-default hints, and hints are a way to tell the libc to do things differently. So even if your Go application are actually using the glibc, the behavior you will see might be different. And this is one of the things that we found the most surprising at the time.
Yeah, so you're going to see different behavior if you take I don't know, Python application and it's running on Ubuntu, it might behave differently when you run it on Alpine. And if you take a Go application, that could behave yet another way, and that could vary whether or not it's using cgo or just regular Go. What kind of variations are you going to see in the DNS behavior from these different resolvers?
So one of the ones that we face the most, because I mean, you remember when my example, when I was showing that for www.google.com, we were doing 12 queries, is the fact that half the queries are for IPv6. And if you're not running IPv6, which we're not, you don't want these queries, right? And so we tried very hard to remove IPv6 queries because, of course, if you remove IPv6 queries, first, you decrease loads on servers, which is important, right? Because you basically divide it by 2. And second, you avoid a very bad bug in the kernel connection tracking system, where if you send 2 packets on the same port and IP combination over a very short time frame, there you can hit a race condition in the contract in the kernel where the second one is dropped.
Wow.
And some resolvers will do IPv4 and IPv6 queries almost in parallel using the same port and IP combination. And if they happen to happen in the same, like 10 microseconds, for instance, the contract might drop the second one, which leads to the behavior I was mentioning earlier, which is, well, your DNS query is going to take 5 seconds, which is not great.
Yeah. And can you potentially end up hitting that for, it's doing the IPv4 and IPv6 queries simultaneously for each of those different...
Yes, of course.
Yeah.
And the more domain you queries, the more likely you're to hit the problem once.
Yeah. So you could easily end up waiting for, I don't know, 20 seconds or something.
Yes.
If you were unlucky. Yeah.
And this is how we noticed the problem. And we found by looking at issues in the Kubernetes ecosystem that this problem was actually a pretty common one. And so it's been mitigated in the kernel, but you need a pretty recent kernel, right? Because of course it takes a long time for such a mitigation to make it through the kernel. And I actually think it's Martinez that did the fix.
Cool.
Yeah.
Martinez from Isovalent, who
yes.
our audience might remember did a great presentation on WireGuard. So yeah.
And yes, so this one of the reasons we wanted to remove IPv6 was to address this bug. It's less common now because kernel are more recent, and many applications are actually configuring the contract in ways that can mitigate the issue by making the likelihood of hitting the race condition lower. That it was very high in our list of motivations to remove IPv6. And to get back to resolvers, removing IPv6 is actually very difficult because, for instance, in Merzel, in Alpine, we'll always do IPv4 and IPv6 unless you ask the resolver not to, right? If you use default hints, it will always do both. glibc, by default, will only do IPv6 queries if it can find an IPv6 address on an interface. So if you disable IPv6 in the kernel, which we did, you don't do IPv6 queries.
Mm-hmm.
However, if you use Go and CGO, so if you force Go to use a glibc, I mean, you would expect the same behavior, right? No IPv6 queries. But you actually get IPv6 queries because Go has specific hints when it's calling the C implementation of getIDDIRINFO, telling it, well, give me all addresses, which forces glibc to do IPv4 and IPv6.
Right.
And yeah, and the main message here is that this part is weird, right? All resolvers have different ways, and to be honest, I don't think any of them is perfect. They all have different behaviors, different trade-offs, but it will be much easier on yourself if you only have one behavior or two, because the more behaviors you have, the harder it is to understand this type of issues.
So to do that, you might be requiring your development teams to use particular base images so that they're using, I don't know which way you'd go, glibc or muscle, or, but you'd try to.
Exactly.
Yeah.
For instance, in our case, we're recommending everybody uses an Ubuntu base image, not because we don't like Alpine base image. They're great. It's just that we need a base image where we know about, right? And we know the behavior and we can understand what's happening. It's easier on us.
Yeah, it's so interesting with my kind of security hat on. I think, people often want to sort of dictate a base image or a small set of base images that an organization should use for security reasons and to make sure that they've got up-to-date dependencies. But the fact that people also might want to, have an agreed image for DNS reasons is pretty interesting, I think. We got a question in from Magno, and so what is the best way to troubleshoot DNS issues on a Kubernetes cluster?
So it's very difficult. To be completely honest, I found the most useful tool to debug DNS is TCP dump, right? So if you have a problem you can reproduce, you just dump DNS traffic from a pod to the outside world and you look at it. And it's how you find the type of problem I was mentioning before about IPv4 and IPv6, the problem with the truncate bits, these kind of things. Because you can look at DNS packets and you can have an idea what's happening.
Right. I'm going to guess you might be able to use Hubble for that as well, because you would be able to see the flows.
Yeah. I mean, I don't know if Hubble is actually giving information about the type of flags set in DNS packets, right, but it might give you a lot of information about what's happening, of course.
Right, yeah.
And this is for low-level problems, and I'm mentioning this one first because based on the discussion we had before, this is what will give you explanations about what is exactly happening in this situation. However, I'd say what you have to do to make sure that your DNS is healthy globally is to have metrics, right? Look at what's happening, and have metrics on your DNS infrastructure first. So look at number of DNS queries per second, and then break it down by domain, by query type, by answer type. So you have an idea what's happening and you can see if it varies.
I think there's some great examples of some metrics graphs actually in your horror stories, the recording of that talk from KubeCon.
Yes.
There's lots of things where you can see an issue has occurred, you can see it in the metrics, and so I definitely recommend people checking out that talk. We've also got a comment from Eve. Hi, Eve, saying that you can use Inspector Gadget to debug communication as well. And I guess that, I know Inspector Gadget is a sort of front-end wrapper around a number of different tools. I don't know if TCP dump is one of those tools. So if you want to comment on that, Eve, that would be really great. All right. So are there any other horror stories that you want to talk about, or any other kind of issues that you've seen at scale? I know you mentioned about core DNS making core DNS updates safe. That's
Yes.
yeah.
So, yeah, I mean, I have a lot of stories. I need to pick one. So this one is actually interesting. It's very interesting. We decided when we deployed Kubernetes at Datadog that we would be using kubeproxy with IPVS. So remember I told before that we're currently using Cilium, and it has none of the problem I'm going to talk about right now, but this is recent, right? We started 3 years ago.
Okay, so this is a story from before you were using Cilium.
Exactly. And we knew at that time that given the size of the cluster we would be operating, that using IP tables kubeproxy in IP tables mode, which was or is even maybe the default, would be difficult, right? Because of the sheer number of rules you have to manipulate in the kernel. We knew it would be very difficult for us. And at that time, many people were working on a different implementation of kubeproxy that is using IPVS to do load balancing.
Mm-hmm.
And to be honest, we've been very happy with IPVS, except in one case, which is DNS. So the IPVS implementation was very new, and connection tracking. And when you use IPVS, and IPVS, I'm sorry, I mentioned IPVS like it's obvious everybody knows IPVS, but IPVS is a native load balancing solution in the kernel. And it's been used for a long time. I think it's been around for 20 years. And kubeproxy in IPVS mode is leveraging this kind of load balancer to transform traffic to cluster IPs into traffic to pod IPs. And the implementation in the context of Kubernetes was very new. And the challenge with IPVS, it has its own contracting system in addition to the NetFilter one, because it has to track the traffic it's load balancing. And we had many issues due to that. And for instance, where we were doing a rolling update, client pod were still sending traffic to the old IP for too long, right? The backing pod was gone, but it was still part of the load balancing entries in IPVS, and client pod was still sending traffic to this long IP. And of course, since the pod was gone, the DNS core was just dropped.
Right.
It wasn't great. And so we worked very closely with kubeproxy maintainers to tune IPVS and to make it configurable in a way that a core DNS update would be safe. It took us some time to get there, but I think the current situation with IPVS is very, very good. I mean, we're still running it in some clusters, and we can update core DNS without creating an outage, which is great.
So I wanted to actually, maybe we should go back to talking about the multiple Kubernetes clusters question that Marina had asked earlier. I think so. That was really, what are best practices for DNS in between multiple Kubernetes clusters?
So this one is difficult, and I'm going to give you an answer based on what we do, and it's not a generic answer. And the problem is, I don't think there is a generic accepted answer to this problem yet. So the way, the first thing I need to mention is every single pod in our infrastructure has a routable IP, right? So, we're here to talk about DNS and not CNI, but this means the IP is accessible from anywhere in our network.
Right.
And we did that because we knew our infrastructure would be so big, it wouldn't fit in a cluster. We have dozens of clusters. And we also knew that using ingresses and load balancer would not always be possible. For instance, we have clients, Cassandra clients in a cluster talking to a Cassandra cluster in another Kubernetes cluster. And you need this communication to be direct, to be efficient, and take advantage of all the features Cassandra is giving, right? And we have this also for Elasticsearch, Kafka, and other applications. This means we can have pod-to-pod IP communication between two clusters, which is great. And that gets us to the question, right? Which is, okay, I can access this pod in these clusters, but how can I get an IP, right? Because my local DNS server only knows about services within my cluster. So the way we've done it for a pretty long time is rely on an upstream project called external DNS, which will register service from a cluster in a global zone managed by the cloud provider.
Okay.
And it's going to do the same thing core DNS does, but instead of updating an internal zone, it's going to use the API from the cloud provider and add entries there for your pods and for your services and the pods backing them. And it's been working. It has worked for us for a long time, but we've had a few issues with it. And the biggest one is how fast is the information propagating, right? Because cloud provider won't let you set TTL, so the time the record can be cached, too high. I mean, you have limits in terms of how low you can go. And some applications want to be updated very fast, because the worst thing that can happen is you do a running update of your service in a cluster, all your IPs change, but your records haven't changed yet. Or they have, but the information hasn't propagated to client yet. And so you have clients with tail entries that can't connect to your service anymore.
Right.
And of course, that's a problem, right? So we've been doing that. We've been mitigating the problem I was just discussing by using mid-readiness time, min-ready seconds in pods, right? So you can tell a pod, in the pod spec in your cluster, you can tell Kubernetes that whatever the readiness prop says, don't mark this pod as ready before a minute, for instance.
To give the DNS records time to catch up.
Exactly, because it has the effect of slowing down your running update.
Right. That's pretty cool. Yeah.
Well, it's not perfect, right? And with more recent version, you can use readiness gates. And readiness gates are additional readiness signal you can put on a pod. And basically, a pod is considered ready if its readiness probe is okay, and if the readiness gate has been cleared by some controller. And so you can say, I have a readiness gate for external DNS, for instance, and the gate will be cleared when the entry is in the DNS zone of the cloud provider, which means the pod won't be ready until you've successfully updated the records on the cloud provider, which is better than waiting X seconds, because you never know how many seconds you need.
Right. Yeah. So you can kind of dynamically figure out when you're ready rather than just waiting for a minute. Yeah. Speaking of the cloud providers, it reminded me of another issue that I'm sure I learned from either talking with you or one of your talks. The rate limiting that cloud providers will often have that can affect the DNS queries that you're allowed to make to the cloud providers DNS server, and the whole UDP versus TCP.
So this one was definitely a fun outage too, right? So you remember I was saying before that DNS can use either UDP or TCP. And at one point we decided that we were going to standardize on TCP because, I mean, it's far less likely you will lose packets using TCP, because TCP has all these retries built in, and it will retry before 5 seconds, which is better. So we were doing that everywhere with very good results, except when you enabled it for the upstream provider, so for the zone that is not managed by the cluster. And because for all the other records not in the cluster, we forward queries to the cloud provider resolver.
Do you have a diagram of that? I think you might have.
I think I do, yes. Yeah. Right. Let me share my screen.
think this is worth seeing in a diagram.
Yes, you're right. Oh, yeah. I actually, maybe I have it. Oh yeah, this one. This one is simpler. I'll get to the other one afterwards. So this is a diagram here, right? You see the DNS pod is watching the API server for service in the cluster. And for everything else, it's sending queries to the upstream resolver, which in our case is what the cloud provider DNS. And when we updated this communication to use TCP, we had a lot of issues. And the reason is, in this specific provider, there's a rate limit for DNS queries, which is not expressed in queries per second, but in packets per second. And switching from UDP to DNS meant the number of packets was multiplied by 10, basically, for the same number of queries. And so things that were working completely fine suddenly broke. And so we had to revert to TCP for the communication on this arrow here.
I think it's so interesting that it just doesn't really make sense. Why do that rate limiting on a per packet basis? I don't know. We got a question in from Marino. Are there efforts to find ways to enhance DNS for scale? And are there any open source projects we should follow? I guess XDS might be something to talk about.
So yes, I mean, there are two things we can talk about on this exact topic. The first one is this slide I was about to share before, which is what we run now. So this is detailed, and this is exactly with UDP and TCP. But what is important here is our containers are not connecting to the DNS service directly anymore in our setup, and this is what most people are doing now. So to decrease the load on DNS servers, we actually put a DNS cache on each node using a daemon set. And so this service is on the host, it's binding a specific IP, and we configure our containers to use this IP as a resolver, which means we have local caching, which is great, right? Because if you have an application performing the same queries hundreds of times per second, you're not going to hit DNS pods, right? You're just going to serve them from the local cache, which is far more efficient. And this is extremely helpful. An additional very good thing about this design is you can actually do routing on the local DNS itself. So on the local cache, you can say queries for the cluster domain you send to the DNS service upstream, which is the normal thing we do. But what you can also say is for queries outside of the cluster domain, directly use the upstream provider. And this also helps decreasing loads on the DNS infrastructure, because we directly connect to the upstream provider, in our case, the resolver from the cloud provider. And yes, and you were mentioning XDS, which I think is the last thing I have, and I can talk about that unless you have a question on this slide.
I think let's talk about XDS, because I think that is an interesting sort of future thing to talk about. And then I have one more question I want to ask before we wrap up.
So I mean, we've been talking about DNS for a while, and DNS is great for very stable records. I mean, it's been designed for records that have a TTL of hours or even days. And this is what is usually used everywhere on the internet, right? If you query for a domain name, usually you get an answer, and this answer will be valid for hours and maybe sometimes minutes. However, in the case of Kubernetes, the backing infrastructure, like the pods backing a service, can move fast, right? You can add pod, remove pods through running updates. And so there, a TTL of minutes or hours won't do it, right? You can't. And so you have to reduce TTL. And that mostly works, but you need to have a very low TTL. And so you'll see many design where people use TTL of 5 seconds, which is the default of core DNS, for instance, for services in the cluster. But of course, I mean, DNS was not designed for very low TTL. It was designed to scale based on caching. So if you reduce the TTL, you lose one of the biggest advantages of DNS. And also, for this to be efficient, you need your application to know about the updates, which means you need your records to be valid for a very short amount of time, but you also need your application to be pulling for this information very frequently. And so something we've noticed and that everybody has been noticing is that TTLs tend to go down and number of queries tend to go up as applications tend to query DNS more often to have the most up-to-date view of the world. And that takes us to XDS, which is basically a way to do things the other way. Instead of pulling for this information, we actually subscribe to a service that will stream changes to us. And let me get to the slide showing this. And so here is an example, like it's of how it works. And many people are moving to this type of design for the reasons we've been talking about in the last hour, right? So the very high overview is you have a control plane that is similar in many ways on how a DNS control plane would work, except the XDS service in the middle of this slide is not only serving queries, it's a gRPC interface, and it's going to stream changes for the service you care about. And so your application can connect to this and be notified if the IP set backing a service is changing. And in terms of context, this has been developed in the Envoy ecosystem. So Envoy is a proxy that is designed to be very dynamic in terms of how it's configured. And it can get data out of this XDS control plane. And I realize now that I've been using the XDS without saying what it means. And so XDS actually means any, so that's the X. And DS is discovery service.
So you can discover a lot of things that are not just
exactly.
IP addresses, yeah.
So the most common thing you discover is endpoints. So EDS is an implementation that is similar to DNS, but you can have a lot more. Like in the case of HTTP, you can configure HTTP routes, for instance, right? So you can configure Envoy to send traffic to different backends depending on the HTTP route that is used.
Good. And yeah. I'm just going to jump in and say, Marino saying this is super cool, and I'm not sure how to pronounce your name, but I'm going to say Bojanche, saying XDS everything. So.
And yeah. I mean, I'm sure you've heard about. I mean, people have heard about eCHO, and eCHO is a way of implementing that, right? This is generic, but eCHO is one way of implementing service mesh, and it's doing this under the hood.
Right. I think XDS is definitely something to watch. Right, we are very much running up to time, but I did have one other question I really wanted to ask you about before we wrap up, which is, what should people be doing, SRE teams be doing in terms of instrumenting their clusters to spot DNS problems and hopefully avoid them?
So, I mean, we chatted about it a bit before. Like the first thing is instrument your DNS pods, like look at core DNS metrics and make sure that they look okay. Also, something that we've noticed that is important is also look at metrics on the hosts backing DNS pods, because when you have so many queries, you can hit limits at the host level, not only in the pods, like a number of entries in the contract, for instance, right? These kind of things. And the last one, and it relates to the discussion we're having about Inspector Gadget before and a Hubble, is seeing what's happening in core DNS pod is important, but it will not show you everything. So the most interesting part is actually looking at what applications are seeing. And so try to have this view. And this is where tools that instrument DNS queries, like that parse DNS queries and give you metrics on DNS queries from the client perspective, are extremely useful. And I know Hubble does that. In Datadog, we also have network monitoring and DNS monitoring doing the same type of thing to give you information about what your applications are doing and seeing, which is very important, right? Because if an application comes to you and say, in some cases, I'm losing DNS queries, looking at your infra that is serving tens of thousands of queries per second won't help.
For sure.
Because it's very hard to know what's happening there, right?
I know we're pretty much up to the hour, so I feel like we're going to have to call an end to our wonderful conversation. I feel like I've got about half a page of questions that we haven't had time to cover, so I might have to get you back onto eCHO again in the future, Laurent. But thank you so much for sharing your knowledge and expertise today with us.
It was really a pleasure.
And thank you everyone in the audience for joining us today. I just want to mention that next week we will have a new host, which is Duffy Cooley, who joined Isovalent just this week, and he is going to be hosting eCHO next week. So I'm sure some of you will know Duffy from the community, and it will be really great to have him on board with us in the eBPF and Cilium community. As usual, the show notes will be in the GitHub repo. Thanks again for joining us, and I will be back in 2 weeks. Duffy will be here next week. Thanks for joining us.